Okay, so this morning in our learning seminar, Fred Galetto from Cleveland State is going to talk about the affine Buchberger-Muller algorithm.
All right, so I wanted to put this on the board because I want it to be visible the whole time, but you don't actually need to worry about that just yet. So let me tell you the problem that we're trying to address. So we're gonna let X in some affine space be a finite set of point. And K is some field. Doesn't really matter what it is for the purpose of this talk. So what we want to do is we want to look at the polynomial ring. It's the coordinate ring of this affine space. And we would like to know the defining ideal or the vanishing ideal of this set of points. We would like to find generators. And even better, maybe if you have a particular monomial order on your polynomial ring, find a Gröbner basis. Okay, so find, let me say, a Gröbner basis of the vanishing ideal of this finite set of points. Okay, so, all right, so suppose that we give the points some names, P1 through PS, and maybe one of these points, PI, has coordinates CI1 through CIN, then the vanishing ideal of just that point is easy to describe because all we need to do is something like this. We have the maximal ideal. And then if you can do that for all the points in order to get at CI1 through CIN. Oh, yeah. Sorry, you need the coordinate. Thanks. So to get at this one, now this is a union of the points. So we intersect the defining ideals. Okay, so this is one way to find generators for this ideal, right? And in fact, with the theory of Gröbner basis, you can intersect two ideals. If you know their Gröbner basis, you can find the Gröbner basis of the intersection. So you could do this over. I think you can also do intersections that are not just two ideals. You can do them all at once if you set them up right. But anyways, you can find the Gröbner basis this way. So it turns out, unfortunately, that doing things this way is not the most efficient way. In fact, it can blow up if you have a lot of points and take a lot of time. So instead, there is a more efficient way to find the Gröbner basis of this ideal, which is given by this algorithm over here. Okay, so the version that I'm presenting here is from the from Computational Commutative Algebra 2 by Kreuzer and Urbiano. And I wanted to start with the affine one. Really, I guess maybe the interesting one is the projective one, but I wanted to start with the affine case because really it gives you a sense of the operations that you have to perform. And then the projective situation, which I'll talk about later, requires a tiny little bit more on top of that. So basically, half of the talk is going to be one example of this, but I really want us to walk through and do the computations to see exactly what happens. So I chose a set of points. So this is going to be my long example one for the affine case. I chose 4 points, but in A2. So 1, 1, 1 minus 1, minus 1, 1, and minus 2, minus 3. And I'm working over the rational numbers. And we would like to find the Gröbner basis of the ideal of the set of points inside QXY. And let's say we do the reverse lexicographic order. So we do G rev lex or deg rev lex, however you want to call it. Okay. All right. So now we start computing.
You have to pick your order at the beginning.
I think so, yes. I think the way it's set up here, you need to pick it at the beginning.
It's on a specific order you have to pick. So, it's not like this algorithm only works for one order.
No. It works for any order. You pick your order. But I don't think we want to do lex. I don't know. Probably not. Okay. So, all right. So I'm just going to go through. At the beginning, you start by forming this G that eventually is going to be the Gröbner basis as an empty set. There's also going to be another set S, which collects some polynomials that you need throughout to form the elements of the Gröbner basis. I say sets, but really we should think of them as sequences because we're going to add stuff in order. We're going to append the stuff at the end of these. So maybe lists if you prefer. Then there's going to be a list of monomials, and this starts out with just one. Then there's this is like a curly S. Yeah, right. So these are both going to be lists. Okay.
Okay, so it's going to be something that gets changed as.
Yes, we're going to append stuff to both of these. Yes. Yes. So maybe a better way to do this is. No, so you can actually cut this out to save a little bit of time. You can, in the algorithm, also keep track of another set where you put the standard monomials. I cut it out to make it a little bit shorter, but yeah. No, so you'll see these are just some polynomials that whose combinations will give you the terms of the Gröbner basis once you have enough of them. And then there's this M, which is right now. So we have 4 points, so there's going to be 4 columns, but we don't have any rows yet. So this is going to be a 0 by 4 matrix for now. We're going to append rows to this matrix.
That's a 0 by S matrix and S number.
Correct. Yes. Yeah, I'm using the notation from here, P1 through PS. Yeah. Okay. So then, all right. So basically, everything revolves around this L in the sense that when this L becomes empty, you're done. Okay, but it's not empty now. So what you do is you start taking things out. You take the smallest element you have in here and you remove it. Here we have only one, so I'm going to call that T equal 1. And then L is empty for the time being, but we're going to add some stuff to it. So now we have this first monomial, which is the constant one, and we're going to evaluate it at all the points. Okay, this is not going to be very interesting, but it gives you a vector. So this is what I denote in here as the monomial T evaluated at all the points. Okay, that vector itself is not what we need. We're going to reduce that in the sense of row reduction against the rows of the matrix M, which at the moment is empty, to get the vector we care about. So really, the vector we care about here is just all ones, really. Let me just write directly V1 through V4 is 1, 1, 1, 1, which is non-zero. And now you get into one of these two situations that are step 4 and step 5. We'll see this later. If that vector becomes 0, you have found a new element of the Gröbner basis. That's not the case. So what we do here is basically right now we don't really have much. So we take this row and we append it to the bottom of the matrix M.
That's different from the set, that's why, right?
So when I go to step 2, I have to take L equal 1, that contains only this, and I have to extract the smallest monomial in the monomial order. Yes, so I take it and I have this kind of variable T that I set it equal to the mean. Yeah, no worries. Yeah. All right, so let me see. Then here M finally gets a row, 1, 1, 1, 1. And then the set S that contains these temporary polynomials right now there's not much going on, but you append to it a polynomial that depends on this reduction here. Right now it's just the monomial 1. And then finally, what you do in this step is you had this t or this monomial over here, you multiply it by all the variables, and you repopulate L with new monomials. So in this case, 1 times x, 1 times y, so I have x and y. I like to write the y first because I want to have the minimum in the order first, but that's not crucial. Because when I go back to step 2, I'm going to have to extract the minimum again, so y will come out first. So at this stage, this is probably still a bit mysterious, but I think if you see a few more steps, you will start seeing why this works. So essentially, we have to do this a few times until we actually get enough rows for m. And then our vectors we will be able to reduce to 0, which will trigger step 4, which actually gives us elements of the Gröbner basis. Okay? All right. Questions? Okay, maybe let me, I'm probably gonna need a lot of space for this, so let me continue here. So now we're back to step 2. In step 2, we take the minimum, which is y, and then we remove it. So we just have x left inside L. We have to evaluate this t at the 4 points. Now the monomial is y, which means we take the y coordinates. So it's going to be 1, minus 1, 1, and minus 3. And this is the vector that we have to reduce against this matrix over here. Now, okay, so not a lot to do really, but so really the only thing we'll be able to do is make this one into a 0. So 1, minus 1, 1, and minus 3, minus the only row we have in M gives you 0, minus 2, 0, and minus 4. Is that right? And this is non-zero. So that means we have a new row in the matrix. We have a new element to append to this S. Now this is where you start seeing how you get polynomials in here. So the element that I have to append is coming from this reduction over here. Okay? Now, in the reduction, I used this vector, which was coming from evaluating the monomial t. So this corresponds to having a y here. This one, on the other hand, corresponds to, this is the first row of the matrix, which corresponds to the first element of S. So this is going to be a 1. So the polynomial I have to append here is y minus 1. And I think that's it for this step. Oh, no, I have to repopulate L. So I have to repopulate L, which means I have to take y. So L already contains x, right? So I have to take y and I have to multiply by x and multiply by y. So in principle, I would do this, but it's not going to be correct. See, xy is a multiple of x, so we don't need to consider that actually.
I have a question. Maybe you'll get to this, but you have these coefficients, the AIs there in your step 3, right? Your reduction there.
Yes.
What would you like?
Oh, in this case, it was a -1, so I put so it's like if I had a -2 here, then it would be -2 times this polynomial.
So how do you pick these AIs? Like why couldn't
Oh,
we have
because I want to reduce, so I have this vector, and because I have a leading 1 here, I want to put a 0 in here. So I have to choose the -1 to get a 0 here.
you want to somehow get something close to like that program?
Yeah, exactly. So you want to think that this gets added as a second row in here, and then you row reduce. keeping the previous rows.
Oh, okay, so you're keeping track of row reduction.
Yes.
So the next one here.
Yeah.
So why are you actually removing X, Y from the list? Because you will now be taking it out and then it will go away later on, or is it just
All right, let's see. So it says I have to take it out because it is a multiple of something I
X,
already
right?
have,
Another
right?
element, yeah. So you're sort of
Right.
replacing L with the minimal generators of that minimal ITL.
Uh-huh.
Right? Which is fine, and so you can actually do it here. But then later on, you're going to be, when you take X out, you're going to be adding X, Y yet again.
Right. So I think the advantage might be that if when I work actually in the next step, I'm going to work with this X. If I got a polynomial that vanishes on the points from that, then I wouldn't need to reconsider X, Y.
Right, exactly.
Uh,
But that would then go away in step 4.
right.
So,
Maybe just to keep it small.
so maybe it's just to keep it smaller. Yeah, so it's easier.
Okay, so bear with me because we need to add 2 more rows. Then it will be a 4x4 triangular matrix with non-zero determinant, and then everything else will reduce. Let me keep going here. So now we have to go back to 2. We take the minimum of the set L, which is X. We remove the X, so we have Y squared left. Let's see if I can do the reduction here. So I have to evaluate X at the points. So let me see if I can squeeze it in this way. So V1 through V4 is taking this X and evaluating at those points. I get the X coordinates, 1, 1, -1, and -2. And now I have to row reduce this against the previous M. And so I'm not going to try to do it again. I already did it once. So I have to subtract the 1, 1, the top row to get a 0 in the first place. And that's probably it. So this will give me 2 zeros actually, right? Yeah, so I guess I'm lucky that way. I know.
Second row is 0 minus 2, 0 minus 4. But
No, you can leave it like that. Yeah. Maybe you can.
it's probably not.
This is one of those things that might actually just result in different coefficients that you put in front of your polynomials. This will actually output the reduced Gröbner basis. But
If you divide by the second row, then like the second row will corresponds to half Y instead of just Y.
yeah. But then again, it doesn't quite get back to the vector you obtain from evaluating the monomial. So maybe you don't actually want to do that.
I guess you'd have to change the polynomial.
Yeah, you would have to change that too. Yes. Okay. So what polynomial results from this? This was the monomial X. This was still 1 from the first element of it. First row of M corresponds to first element of S. And so now we have 1, 1, 1, 1, 0, -2, 0, -4, 0, 0, -2, -3. S also grows. We append X minus 1. And then we have to repopulate L. So what is it? X, it will be X squared and XY. Right? And I think we take all of them. All right.
And that was just because you chose the other A.
So it turns out that to row reduce in both of these cases, I only needed to subtract one of the rows. I think the next one coming up, no, not even the next one. Interesting. Yes. Yeah. There will be one a little bit later. Okay, so where are we at? There. Okay, so now we have to keep going back here. Take the minimum. This is y squared. L has this stuff left. So we're gonna have to evaluate again. Again, let me try to do the V already. So the evaluation of y squared at the points gives me 1, 1, 1, and 9. And when I row reduce, again, just the first row is going to suffice because it's going to give me 3 zeros. But the good news is that after we add this to the matrix M, we won't need to add anything more. So yeah, this is non-zero. So we go to step 5, and our M becomes 1, 1, 1, 1, 0, -2, 0, -4, 0, 0, -2, -3, and 0, 0, 0, 8. S gets one more thing. This is y squared, and this is 1. And in L, let's see, we still have xy and x squared, but now we also need to throw in x times y squared, which is actually a multiple of this one, so we don't need it, and y cubed. Okay, so thank you for your patience. Finally, we will get an element of the Gröbner basis. So xy is the next minimum. In fact, I think now for every monomial, you get one. So the vector of the v's is obtained by evaluating xy. So 1, -1, -1, and 6. And now see how we can reduce this to 0. Subtract the first row, and that will give you 0 here. Then you actually get a -2, which means we can subtract the second row. And then let's see. Then we would have -1 and -1. That's a -2, which means you can subtract the third row to make that a 0. And finally, I'll tell you, you can check. It's -3/2 times the last row. So this vector is a linear combination of the 4 rows. I mean, obviously it is a linear combination. You just have to figure out the coefficients, right? We have a -1, -1, -1, and -3/2, and this is 0. So what does that mean? That means that, remember, every one of these vectors corresponds to either a monomial or a polynomial. So here we had the xy. Here we have a 1. Here we have y -1, x -1, and y squared -1. So if we take the linear combination corresponding not to the vectors, but to the polynomials, then we actually get something that vanishes at all the points. So then finally we go to step 4, and in step 4 we add something to G. So it's that combination written up there, right? So xy -1 minus y -1 minus x -1 and -3/2 y squared minus 1. You probably want to simplify this a little bit. So this turns out to be xy is the leading term, negative 3 over 2y squared minus x minus y plus 5 over 2. So basically, I think that the way we constructed this is by taking an appropriate linear combination of monomials and polynomials designed to vanish at the points. So I think maybe it's okay if I don't do the rest of this. Hopefully, you believe me that even if I keep doing this for x squared, I'll get something that will reduce to 0, and even with y cubed. So you get 3 polynomials. If you want, I can tell you what they look like. So skip to the end. Oh, let me just say though, how do we repopulate L in this case? L has x squared and y cubed. And then what do we have to do here? Oh, no, just remove. So there aren't any multiples of xy. So I guess we keep it like this and keep going. Yeah, okay. So skip to the end. G has that thing. Xy minus 3 over 2 y squared minus x minus y plus 5 over 2. There's another quadratic x squared minus 3 over 8 y squared minus 5 over 8. And then finally, y cubed minus, or sorry, plus 3y squared minus y minus 3. I guess we can see that these other 2 polynomials in the Gröbner basis have respectively leading term x squared and y cubed, which is what we had left in the set L. And maybe one interesting thing here to notice is that, in fact, we have 4 points in affine space. So you can probably imagine that they can be obtained by intersecting 2 quadrics, which are these 2. But we want a Gröbner basis. And if you want a Gröbner basis, we actually need this last element also. Okay? All right, so, and now let's go into details. I'm not giving you a proof, but let me tell you briefly the idea. So, basically what you would do to prove this is you have to show that when you go through, every time you add something to this set G, it better vanish at all the points. But that is by design, right? As we have seen, these polynomials are designed to vanish. Also, what else? So you want to, you have to keep going, and you do that by this step over here, right? So whenever you have a monomial, and that is coming from step 5, so it was some reduction that did not lead to 0, you multiply by all the variables and you get new candidates. But eventually, this is a set of points, so it's a 0-dimensional ideal, eventually will contain all monomials of a given degree, right? So eventually this thing will have to be emptied out, and that's when you stop. Okay. So I will actually say this, that I think Mike, and was there anybody else involved? You have this coded in Macaulay 2. It's been coded for a long time, I think. And then
But I don't know if it's done as well. There is one step here that looks like it might take longer than, like, you have to combine all these polynomials S's at every single step, right? For every degree D, you have this combination of
Mhm.
lines that you have to make into the element G.
yes.
For every Gröbner basis element, you have to do just a sum of like that number of polynomials,
Uh-huh.
which
I don't know.
I mean, I don't know if there's any way around, but that looks like they have.
Well, somehow I would say we keep reusing those elements of S. So maybe it's worth keeping them
No,
around
no,
like
it
that.
probably is.
Okay, but then I will say also that there are variations on this. For example, so there's a paper by Abbott, Bigatti, and maybe Kreuzer. I forget. There are other people. They've actually done some analysis of how well this works, some complexity analysis. There are also, they say actually that the coefficients in a Gröbner basis for working over the rational numbers can be really large. They can explode, and that can slow things down. So they actually do a version of this that uses the Chinese remainder theorem. So you do it modulo various primes, and then you combine everything. It's pretty nice. And there are versions of this that work not only for points, but really for any zero-dimensional schemes. So you could do fat points, or you could do something else. Basically, instead of evaluating monomials, you need to find an appropriate linear operator to use to give you these vectors that then you're going to reduce, essentially. I don't remember the paper. I don't think the book does it, but all right. So then, if this is okay, let me just give you what changes in the projective version, because that is probably the more interesting one. So I'm going to hide this.
I just have a question about the modular.
Yeah.
Chinese version.
Yeah.
So can one get bounds on the size, of the coefficients in the ideal ahead of time, or do you just sort of do it on various primes and then until it sort of stabilizes?
I only skimmed through that part. I cannot tell you precisely. I'm not sure you can get the bounds ahead of time, but I'd have to look again.
Bigger than the bound and then work with that.
Actually, I guess maybe if you happen to have the actual polynomial that you think are correct, in this case, you can actually check, right? Because all you have to do is plug in the points, and if they're zero at all those points, then the ideal, since it has the same Gröbner basis, I think that that it would probably have to. I'm not sure, but anyway.
All right. So now suppose you want to do something similar, but X is a finite set of points in Pn over some field. Right? Now, if you're really lucky and all the points lie in the same affine chart, then you can do the affine version and then homogenize, but that's probably not always the case. So obviously you can also still do something like that, right? Your point will have its coordinates. You form another row of variables. You take the 2x2 minors. That gives you the ideal of one of the points. You intersect them, but you're running the same issue of complexity. So instead, there is a version, a projective Burger-Muller version. So here the polynomial ring will have, well, I say Q, I should have said K. It will have x0 through xn. And again, we're still looking for a Gröbner basis of the vanishing ideal with respect to some monomial order that is fixed ahead of time, whichever one you like. So I'm going to tell you the essential thing that changes. So what happens is that you can't just do what we were doing earlier when you have one of your monomials T multiplied by all the variables and eventually hope this set will empty out, because this is a zero-dimensional set, but that means the ideal is going to be one-dimensional in here, right? So instead, you have to basically proceed degree by degree, or another way to say this, the set of standard monomials is not finite, right? So you have to proceed degree by degree. And so the main question is, when do you stop? So so actually that paper that I mentioned by Abba Bigatti and other people has different ways of talking about stopping criteria, but I'll give you an easy one here. That's the one that's given in the book. So the Hilbert series of the set of points X is eventually constant. Should I have said Hilbert function? Yeah, Hilbert function is eventually constant and equal to the number of points, which is S. So how do we modify the algorithm? We proceed degree by degree, and we stop when we have something that looks like this. But if we take the initial ideal, we can easily compute a Gröbner basis and then find that it matches what we expect for the set of S points. So set, I'm gonna give you a summary of what changes. Set D equals 0 and L equal 1. Follow the Buchberger-Muller algorithm until L has been emptied out. Then let S, let me call it, well, I was using the notation in the book, so this is not a curly S. This is our polynomial ring, R, modulo, the ideal generated by the leading terms of your Gröbner basis that you're constructing. So it might not be the final answer just yet, but you do that. And then if the Hilbert function of this quotient is equal to S for all I greater than or equal to D, you are done. You can return your set G, which will be a Gröbner basis. Otherwise, you go to the next degree. Increase D by 1. And you set L to be the monomials of degree D. Well, except you already know some you don't need to check, so you can leave out stuff that's multiple of these things. Not in this ideal. And you keep going.
Degree D. Degree D.
Oh, thank you. Yeah, so we have increased D by 1, so then it will be monomials of degree, the new G.
So up here, then, when you're running this thing, you don't keep adding elements to L.
Right,
So
exactly. You just remove until you have to go to the next degree. Okay, so, and then again, the idea, the proof goes through the same way, same idea as we said before, but now you can use this as a stopping criteria. But that paper that I mentioned has something that's a little more sophisticated, but probably a little better, maybe allows you to stop a little sooner, I'm not sure. But also you can phrase this in terms of the regularity of the ideal, I guess. Once you have, I think, reached the degree that is the regularity, then you can stop. I think that would be another way of saying this, essentially. So then maybe if it's okay, 10 minutes, I don't really have other material, maybe show you some steps of what that would look like for a projective example. So let me go back here. Okay, so this time I only did 3 points. 0, 1, 1, 1, 0, -1, and 2, 1, 0. This is in P2. So we're working over the polynomial ring Q, let's say XYZ, or X0, X1, X2. And again, let's say we take the graded reverse lexicographic order. Now, okay, let me cheat a little bit here. In principle, we have to start with d equals 0, right? But there's no constant that vanishes on all the points except 0. And also d equal 1, we can skip because the points are not collinear.
Sorry, can we switch the camera, please?
All right.
Okay, so
But so each time you throw out the matrix out?
yes, that's right. Every time you switch to a new degree, you start from scratch. You empty out, I mean, you keep the G around, right? But the S, you have a new set L, the S is empty, the M is empty. Yeah, so that thing we did earlier, you would have to do possibly many times depending on the degrees. So maybe we'll just do one run in degree 2, okay? So again, for the reasons I said, let's start with degree 2. So here I have to populate, well, at this point, there's nothing yet in the Gröbner basis. I have to empty out this set L. And here I take all the monomials of degree 2. Again, I just order them from the smallest, but that's because we have to extract the minimum. And then M is a 0 by 3 matrix, 3 points, so 3 columns. And now we keep doing what we were doing earlier. So let me take out T, which is the smallest element, okay? And that means L is gonna have fewer things. Let me just abbreviate like this. Now that we have this monomial, we can evaluate it at the points and get a vector that we're gonna reduce against the rows of the matrix, except there's nothing really to reduce here. So Z squared, so that means 1, 1, and 0. And so in my step 5, this is clearly not 0, so I have to go to my step 5, where M has acquired its first row.
Yeah, right.
Okay. So M is this, and then we probably want to put something in here in S, which is Z squared. And then L, yeah, like before. No, YZ. Like squared. So we only need to do this 2 more times to get that full rank matrix. So let me go back to 2 and say T is YZ. Then L has whatever's left. So step 3, we get a vector by evaluating, what's the T? YZ at the points. And in this case, I think you get 1, 0, 0, right? And then we have to reduce against the row that we already have. So that will give us 0 minus 1, 0, which is non-zero, and we get a new row. We have a new element in S also. Now, what are these? This was coming from Z squared, right? And this is coming from, no, sorry. This is coming from this. What am I saying? This is coming from YZ. And this is coming from Z squared. Yeah, okay, thank you. So this will be YZ minus Z squared. and then L is the rest. Okay, so one more. T is XZ. L is the rest. When we evaluate and reduce, let's see, what do we get? XZ here is 0 minus 1, 0. Actually, sorry, we get an element of the Gröbner basis, right? Because am I doing this right? XZ, 0 minus 1, 0. Yes, and we already have this row. So we actually get something in the Gröbner basis. Okay.
Why in the last two of the previous blackboard, L became the XZ instead of, you have just removed YZ.
Yeah, so I always take out the minimum and keep
Also,
the rest.
the next one.
Uh,
Yes, sorry.
that's okay.
Sorry. My
No worries. But let me show you what happens here. G is this, we're appending something to G, right? So that would be this monomial is XZ, and then this thing is the second element we had in S. So minus YZ plus Z squared. And you can verify that this vanishes at the 3 points. So in the interest of time, maybe, instead of doing everything else, let me just say, so L here has the 3 monomials left. I think the next one, Y squared, gives you something that doesn't vanish. No, sorry. Yeah, it gives you something that doesn't vanish, so you get a third row of M, which means the other two will give you something that vanish. Okay, so if you run through until L is empty, then you will get, and where should I put this? Maybe I have to put it over there. I just want to show you this partial Gröbner basis, what that looks like. So skip to L empty, and you get that thing. So XZ minus YZ plus Z squared. The next one you encounter is XY minus 2Y squared plus 2YZ. And the third one is X squared minus 4Y squared plus 5YZ minus Z squared. So here we have our leading terms. And what happens to the ring S, which is Q XY mod XZ XY X squared. So if you mod out by the initial ideal, then you get a quotient that has a Hilbert series or a Hilbert function that in degree 3 is equal to 4. Let's see if we can find what survives in degree 3 that's not a multiple of these. I guess you have y cubed and y squared z and yz squared and z cubed. 4 things. So this is not 3, which is not the number of points, which means then we have to do this, right? We have to go to the next degree, which I won't do, but actually if you go to the next degree, then that's where you get, I think, 1 or 2 more elements of your Gröbner basis. So very, very briefly, let me just finish saying this. I learned this some time ago. I can't know it very well, but I looked at it some time ago. And some ideas that I always had about this, specifically about the projective case, is, well, is there any way that while you're doing this, you can simultaneously get some information about syzygies, for example? Because you're constructing a Gröbner basis. So maybe there's something you can do there, and maybe even start building a minimal free resolution or a free resolution. Another thing that Adam was suggesting is, well, what about not necessarily looking at points, but looking at things like lines? So if you have that, let's say you have a finite set of lines, and you can describe a line by the 2 points it passes through, then if you want to do something like what we're doing here, basically in this step, you have to evaluate something, but now you can think maybe your line is parametrized, right? Like A plus TB, and then you have to do this evaluation in a ring that has one variable, the variable for the parameter, but you can still check if things vanish. But then, of course, if you're doing this projectively, when do you stop, right? What is the right criterion? You might need to know something about the Hilbert function or the regularity, something else. So I'm gonna stop here.